Alright, so in class we talked about how to apply this Bronsted-Lowry definition of acids and bases to this idea of finding or identifying our conjugate acid-base pairs. So this is meant to go over that in case you missed it or didn't understand it the first time. And so if you remember or have already taken notes on the first page and the top of page 2, the Bronsted-Lowry definition is all about proton donors and acceptors, what's happening to the proton. And in terms of our acid-base reactions, protons can be regarded as these H+ ions. So what we're going to fill in here is just the Bronsted-Lowry definition of acids and bases. So acids are donors, proton donors specifically, and bases are proton acceptors. And we're going to use that fact in these reactions that you see down below in order to classify substances as acids and bases. And what we kind of have to do here is look at the reactant side and product side as kind of a before and after snapshot of the reaction. That's what it is. The only thing is, before and after, we don't get to actually see the donating and accepting happen. We just get to see what there is before the reaction, before the H's are moved, and what we have after. And the only difference between some of these substances are going to be a single H that is gained or lost. So we need to see that and decide whether that substance was donating or accepting H's. And just like if your parents asked you to go upstairs and find some clothes to donate from your closet, even if they don't watch you do that, if they've looked at your closet before you donate clothes, and then they look at your closet after you donate clothes, hopefully what they would see is that there is less clothes in your closet if you were actually donating clothes like they asked you to. If you were accepting some new clothes, if you went shopping, or if someone gave you some more new clothes and they had looked at your closet before and after, they would see more clothes in there. So even if they didn't see you donating or accepting the clothes, by looking at that kind of snapshot of your closet before and after, they can tell whether you've donated or accepted. And the same thing is going to be true here with our chemicals. So we kind of need to focus in on these chemicals and specific chemicals to see whether they're donating or accepting, which is why the first step in these conjugate acid pair problems is going to be to find your pairs. Find your substances on the reactant side and what they turn into on the product side. So this one, H2CO3, is turning into HCO3. Notice how they're just different by a single H there. And then our H2O is turning into H3O. Once again, the only difference is a single H. We couldn't have our H2O turning into H2CO3 or HCO3. Even though it is a product, it's way different. So this isn't like a classic double replacement reaction where their compounds are splitting in half and mixing back together. The only thing that's moving is a single H. So we found our pairs, and if you don't like color or if you don't have color, even just drawing a line between them can really help find those pairs. Some people I know do like boxes and circles to show which ones are paired up. As long as you take a quick moment to find your pairs, that's going to make everything we do after this so much easier. Because now that we can clearly see, in my case, the green pair and the blue pair, when I'm looking at this green pair, I can see that it started with 2 H's and it ended with 1 H, which means that this had to be acting as a donor because it had more H's before the reaction and less H's after. And the things that are donors are our acids. So this H2CO3 is the acid of this reaction. Now, there's always going to be one acid and one base on the reactant side. So as long as we are confident that that H2CO3 is an acid, then this H2O should be the base. But I would always recommend that you check it. If we look at that H2O becoming H3O, if it is a base, it should have been accepting an H. And it was. It started with 2 H's and it ended with 3. So it must have been accepting a new H in order to do that. So this does back up the fact that H2O is a base here. Now that's half our reaction done, and that's the most important part, because our answers on the product side are basically going to be determined by these answers on the reactant side. As you see up above, our acids turn into conjugate bases, and our bases turn into conjugate acids. So that's the other thing that having these linked does, is it reminds me, well, what is this green thing turning into? Or kind of coming from, if I'm looking at that product side, this green product is coming from my green reactant, which was the acid. So when I'm trying to think what type of conjugate is it going to be, well, that has to be the conjugate base. And this blue thing on the product side is going to be our conjugate acid, because it was created from our blue base on the other side. And bases always turn into and become the conjugate acid. Now, this idea of our acids turning into bases and bases turning into acids, and conjugates, of course, really throws some people off. So I want to take a second to explain what we mean by conjugate acid and conjugate base, to maybe help you understand why they have to switch their description here when they become a conjugate. Just like in like a language class, or I guess even in the English language, we conjugate verbs. We change verbs to apply to different people and situations. I could say that I go to the store, but then I'd have to change the word go if I'm talking about another person, like she goes to the store. I just conjugated that verb to apply to another person. I changed it and the situation that that verb was kind of working and doing its job in. So the same thing is what is happening here when we're conjugating this reaction. We're going to be flipping and changing the reaction's direction. If you notice, all of these reactions on this page have double-sided arrows in between, which does mean that reactants can and do become products, but that there's also a chance, likelihood, that some of these reactions will do the reverse. And the stuff on the right, once we have some of them, is going to react together to form some of that stuff that we have on the left. So if the reaction is reversed, then these substances are going to act like an acid or a base when reacting together. Like I said, those jobs switch, but it kind of makes sense that the job would switch when the direction of our reaction switches. As a simpler example, if you think of these reactions with the proton that's going back and forth between our acid and base, like two people tossing a ball back and forth. When one person is the thrower or the donor, the other person has to be the catcher. That's just the only thing that they can do if there's a ball being thrown at them, is catch it. But once they've caught the ball, if we wanted to reverse that reaction, reverse that action, then the person that just caught the ball has to be the thrower. They're the only person that can be the thrower because they're the one with the ball. Similarly, the base that just accepted the proton, if we reverse the reaction, then they've got the proton and they're going to be the one that's donating that proton to the other substance. Just because the other substance had started life as an acid doesn't mean it can't act like a base when we reverse things. We're remaking that action, that acid there. So everyone's job switches when we reverse the reaction. The thrower becomes the catcher becomes the thrower. Just like our acid becomes the base becomes the acid. And we differentiate between those acids and bases and the conjugate acids and bases because the conjugates are always the products. They're always going to be conjugates on the product side, normal acid and bases on the reactant side. Because what that's telling us is that if we reverse the reaction, conjugate base is if we reverse the reaction, this substance will be accepting H's. If we reverse the reaction, this substance will be donating H's. And that's all that that's telling us. So of course they're going to switch jobs because those conjugates are only going to be acting that way if we switch the direction of the reaction. So hopefully that helps clear some of that up there. Let's do a couple more examples together. First, starting by linking our substances. Here I'm just going to kind of draw a quick little line from NH3 to NH4, just kind of a simpler way of showing it. Could be a colored line or just black and white, as long as we find those pairs, however you want to do it. And if we take a closer look at that purple pair, NH3 is turning into NH4, which means it's gaining an H. It's accepting another H, which means that must be our base, which hopefully means that H2O is acting like an acid here, and it is. It had 2 H's, and then it's ending with 1, so it must have donated an H there. And if we're confident in those answers, which I hope you are, then this purple pair started off with a base, so its conjugate is going to be the conjugate acid, which must mean that our OH here is the conjugate base, because it started off its life, that blue pair started off as an acid. In this next one, I'm just going to use shapes and no colors. So our H2O is going to be turning into H3O, and then this C2H3O2 is turning into just C2H3O2. So our H2O to H3O pair here is gaining an H, accepting an H, so that is going to be a base. And then this probably an acid, and sure enough, I see an extra H at the beginning of this formula that's not there after, so it did donate that H. So this is our acid. And then our square pair here, it started off as the base, so this is going to be our conjugate acid. And that must mean that this is our conjugate base. It seems to line up, match up. So now these last 2 examples on the page are for you to do. I want to see you try those and check those answers with me if you're unsure of them. The one thing I do want to touch on, just because we saw a pattern start to emerge in those first few examples, that I kind of want to quash, because of course it's the very last example that ends up breaking that pattern. If you look at this reaction, just finding our pairs, that's all I'm going to help you with. HNO2 is turning into what on that product side? Hopefully you're saying NO2, because that's the only product that we have there that's just different by a single H. It cannot be H3O, because that has an extra O, but it's missing the N, and it's kind of 2 more H's. It's way different. That is not okay. So we have to make sure that the substances we're pairing up in these pairs are just different from us by a single H. So H2O and H3O, different by a single H. So on the previous ones, we'd always been linking together the first thing on the reactant side with the first thing on the product side, but that doesn't always happen. That's not a pattern you should rely on. You have to look at those pairs critically to figure out what to put together. So with these paired this way in this last one, you should be able to finish it up. And like I said, check your answers with me if you're unsure of them. We did spend a little bit of time in class working on pages 4 and 5, so if you haven't already started working on those, I would recommend it. And I have a couple of quick things that I help people with in class that I think will help you as well. Firstly, on page 4, questions 2, 3, 4, and 5 ask you to explain. And you can absolutely use your own words, but I want to make it very clear what I want included in your explanation. So this is a general kind of structure, formula for what I want you to include in your explanation. Kind of fill in the blanks here for all of these examples. And you'll notice that I have some blanks, and those blanks are going to correspond to what I'm asking you to describe in each problem. So the words here that you see in purple are going to stay the same in every single explanation that you do. The only things that should change are whether we're filling in these red and green spaces based on the strong or weak acid or base stuff that we see. So I'm going to help you out with number 2, because we have a strong acid here. And if something is strong, hopefully the word that you think of is that they completely dissociate, they're completely breaking apart, they're completely ionizing. These are all just different words for dissociate that you should be familiar with. You can just write one if you'd like. And because they're breaking up completely, they're going to be producing lots of ions. And specifically, because this is an acid that's breaking up here, it's going to be lots of H plus ions. So that is the first answer that I want you to write out. And now I want you to pay attention. If it's asking about acids, it's still going to be H plus ions, but once it gets to bases, you need to think about what ions bases are going to be producing. Here with our strong substances, whether it's strong acids or strong bases, we're going to have the word completely and lots of filled in. But when it's weak acids and weak bases, you need to think about what words to replace these red words with and how that's different when we are weak. So hopefully that helps simplify all of the writing you have to do there, and it'll hit the important parts so you can recognize these types of definitions on a test. And then question number 6 at the top of the next page has you do kind of the same thing, but putting it into a drawing. We're just comparing a strong acid and a weak acid here. And like we just said on the previous page, our strong acids completely dissociate, which means all 10 of these molecules that I'm going to be asking you to draw are going to be broken up and separated from each other. In this weak acid, because they only partially dissociate, only partially break up, only a few of them are going to be separate. So in both cases, we're going to have 10 of these molecules, a big circle and a small circle. But in this first one, like I said before, those 10 big circles are completely separate, not touching any of those 10 small circles. In the weak acid, most of them are together, and only a few are separate. Technically, chemists draw the line at 5% or less dissociation. 5% or less breaking apart is what we call something that's weak, which would be like half a molecule. So I just did 1, but even if you did 2 or 3 separate, most of them are going to be together as a full molecule and not ionizing. So hopefully that's not too bad. Draw it as carefully as you can. The molecules don't have to be in the same positions as mine. I just literally tossed them in here randomly. And then in 7 and 8, there are kind of 2 questions you need to be answering. So don't forget to tell me whether these are strong bases or weak bases, strong acids or weak acids. And you should be able to tell just by those arrows that I have there for you. And I want to help you a little bit. I think I did this in the podcast, but in this NH4 reaction with water, NH3 reaction with water, we have it reacting. It's basically being a Bronsted-Lowry base here, where it's taking one of the H's from water to make it NH4, and then water is left as OH minus. But that's a little different than what I'm asking you to do in each of these other cases. So what I want to do as an example is just, I guess 7A. What I'm asking you to do is show the dissociation, show that breaking up of these bases when we put them in water. And we don't need to actually show the water for the rest of these. We just need to show this breaking up. This is a lot like the overall ionic equation that we did last unit. We're just going to find the 2 pieces this is going to break up into. And for NaOH, it's going to be Na and OH. Remember, OH is one of those special groups on the back of the periodic table. We never break those up. So if I had thought that NaO would break off, that's not a special group. If you have 3 or more elements, then you're going to have to check one of those or 2 of those elements are together in a special group. If this was just like HBr, that would be easy to break up. The H and the Br would be separate. But when we got a big special group, we got to make sure to check and make sure we're not breaking up a special group. So if we're breaking off the Na and the OH, we're just going to separate them and give them their charges. So that's going to be Na plus 1, OH minus 1. So I want you to do the same down here with our acids. Remember, acids tend to start with H's. And that should kind of give you a hint as to where these should be breaking up and ionizing. And just double check that you're not breaking up any special groups from the back of the periodic table. And don't forget to classify these as strong or weak once you're done with that.